Welcome back. Let us continue our discussion on heat capacity. In the previous lecture, we have discussed heat capacity at constant volume and heat capacity at constant pressure for a monatomic perfect gas. Monatomic perfect gas will have translational contribution, rotational and vibrational contributions are not there. Now, in case the system which is beyond the monatomic system, there are rotational contributions, and if there are vibrational contributions, then how to account for that we are going to discuss in this lecture. Now, you consider rotation of a molecule. There are two types of rotors we have discussed. One is a linear rotor like carbon monoxide, carbon dioxide, or a non-linear rotor, example is water molecule. We have to again use the expressions which are for the mean energy. CVM is equal to Na del E. I will put R here because we are talking rotational contribution at constant volume. So, therefore, I need the expression for the mean rotational energy. Same way we can use directly equipartition value, that is when the temperature is very high. High temperature means, you remember that we have discussed that HCB is equal to K theta R, and this theta R is the rotational temperature. When temperature is much higher than the rotational temperature, then we have already discussed that the mean rotational energy is equal to kT, which matches with the equipartition value. So, let us use CVM rotational is Na del, the value is kT del T at constant volume, which is equal to K times Na, which is equal to R. This is an easy way of directly putting the equipartition value. Otherwise, ER, which is equal to U minus U0 by N, can be calculated from U minus U0 is equal to minus N by Q del Q R del beta at constant volume. And if the temperature is high, much higher than the rotational temperature, then for a linear rotor, your sigma, which is the symmetry number, will factor into QR is equal to 1 upon sigma H C beta B. And once you substitute this QR into this expression, you are going to get this equal to kT for a linear molecule. So, therefore, for a linear rotor, some examples as I just said, CO, HCl, carbon dioxide, nitrogen oxide, these kind of systems, the CVM R will be equal to R, provided the temperature is much higher than the rotational temperature. However, for a non-linear rotor, you can use the similar exercise, you can do similar exercise, or if the temperature is very high, then you can use the equipartition value and show that the constant volume heat capacity for a non-linear rotor is equal to 3 by 2 R. The mean energy, mean rotational energy is 3 by 2 kT, and the constant volume heat capacity is 3 by 2 R. So, whenever you are talking about rotational contribution, you have to worry about linear rotor versus non-linear rotor. For a linear rotor, the value will be equal to R, and for a non-linear rotor, it will be 3 by 2 R, provided the temperature is much higher than the rotational temperature. All right. Now, if the temperature is not high, then how do we deal with it? If the temperature is not high, if the temperature is lesser than the characteristic rotational temperature, then the expression for mean energy is this cumbersome expression which we have discussed earlier in the previous lectures. You have to take temperature derivative of this, and then the expression for heat capacity will be further cumbersome. Remember that this expression has been obtained based upon the rotational partition function by direct summation method. Once you substitute this expression here, you will get a complicated kind of equation for CVM, and that equation, when you plot then CVM against R versus temperature T by theta R, the limiting value when the temperature is extremely high, when the temperature is so high that temperature is much higher than theta R, then this value is approaching a value, this CVM by R is approaching a value of 1, that is CVM is equal to R. However, when the temperature is not high, you see here when the temperature is close to 0, there is no rotation, the value is mean energy, rotational energy is 0. And in the intermediate temperature, you see how this heat capacity rises in the region when the temperature, experimental temperature, is less than the rotational temperature. I hope it is clear that when the temperature is not high, in that case your heat capacity at constant volume will not be equal to fully R value, but it will be somewhere in between 0 and R. This is how you get. All right. This is rotational contribution. Now, let us talk about the vibrational contribution. We have discussed from time to time that the energy separations are in the following order: translational, then rotational, then vibrational, then electronic, in the increasing order. Translational contributions, as we just discussed some time ago, is always there for a gas at room temperature. Rotational contribution will also be there provided the system is more than monatomic. And if the system is diatomic, triatomic, polyatomic, in addition to rotational contribution, vibrational contributions are also there. Now you look at the comment. It is very unusual for the vibrations to be so highly excited that equipartition is valid, and it's more appropriate to use the full expression for the vibrational heat capacity by using the following expression for mean vibrational energy. What is the meaning of this comment? That the vibrational energy separations are so far apart under normal conditions of temperature that equipartition will not be valid, that value will not be valid. And therefore, it is more appropriate to actually use this direct expression, mean vibrational energy, expression for which we have discussed in one of the previous lectures, is equal to hc nu bar divided by exponential beta hc nu bar minus 1. And we want CVM vibrational is equal to Na into del we need to take temperature derivative of this, and once again the derivation or derivative of this with respect to temperature or with respect to beta, whatever expression you want to use. Now, you see here your expression is in terms of beta. So, therefore, it will be a good idea to use the other form of CV in which the derivative is with respect to beta. So, when you take a derivative of this with respect to temperature or with respect to beta, eventually you come up with CVM is equal to RF square, and in this case m represents vibration. This m. In fact, a correct notation for this will be CVM vibration. Here this m will mean molar. Okay. So, therefore, you can choose whatever way you want to show. And what is this f? F is theta v by t square exponential minus theta v by 2t divided by 1 minus exponential minus theta v by t 2 square, some cumbersome kind of equation. What is the equipartition number? Equipartition number is complete kT, mean vibrational energy. If it is complete kT, that means the value of CVM, full value is going to be R. Here also in this case, if you plot CVM by R versus T, when the temperature is close to 0, there is no vibration. Therefore, heat capacity is approximately 0. And as the temperature increases, you see it reaches towards a full value of R, which is predicted by the equipartition theorem. I hope it is clear. CVM vibrational is equal to R F square. This is what we discussed in the previous slide. Here CVM is R F square, and I am using this over here, where F is given by this, and when you plot CVM by R against T, T by theta V or T, you get this kind of behavior. That means when the temperature is not very high, the contribution is also not very high. So, what we have done? We have now discussed translational, we have discussed rotational, we have discussed vibrational. Translational and rotational. Translational. The value was 3 by 2 R. This is contribution to heat capacity, CVM. We are talking about CVM. Then we talked about rotational. It was either R or 3 by 2 R, depending upon whether the system is a linear rotor or it is a non-linear rotor. Then vibrational. This is equal to complete R. But this is only possible if all modes are fully active. By fully active means the temperature is much above the characteristic rotational temperature or characteristic vibrational temperature. Translational contribution is anyways always there for a gas. So, what about if the temperature is not high? Then you have to see what the temperature is, and the corresponding value of CV can be taken from this kind of plots. Now, there is one more contribution which one can talk about is electronic contribution to the constant volume heat capacity. Once again, if the vibrational energy levels are so far apart, that even under normal conditions of temperature, if the vibrational contribution to heat capacity is very, very small, then the electronic which are further apart, some up further apart from each other, the electronic contribution is negligible then. So therefore, in our normal discussion, we will include translational contribution to constant volume heat capacity, we will include rotational contribution, we will include vibrational contribution. So translational, I will write again here, CVM translational is 3/2 R, fully active. CVM rotational is equal to R or 3/2 R. CVM vibrational is equal to R for each mode, and this is possible if all modes are fully active mode. So therefore, if you are dealing with a monatomic system, let us say monatomic perfect gas, we say that the constant volume heat capacity is 3/2 R. Why? Because when you have monatomic system, the only degree of freedom is translation, and then if the only degree of freedom is translation, we stop here, 3/2 R. And now if we are dealing with a diatomic system, linear, let us say, then another contribution, if rotation is fully active, then another R adds up. So 3/2 R plus R is 5/2 R, right. So this is how the contributions to constant volume heat capacity will increase. So therefore, now if you carefully look at this figure, let us try to interpret this figure. Translational contribution is always there, and what you are doing is you are plotting CVM by R. That means 3/2 R you are consumed here. So 3/2 is always there. CVM by R is equal to 3/2 is always there. So when you start increasing the temperature, you are plotting against temperature. When you start increasing the temperature, rotational contribution will enter in, and when the temperature is much above theta R, another R from here, we are talking about linear system here, another R will enter in. So 3/2 plus R is 5/2 R. Now when you further increase the temperature, we are here at 5/2 R, we are here. When you further increase the temperature, another vibrational contribution will enter in, another up to another value of R. So 5/2 plus R is 7/2 R. I hope this is clear. We started with 3/2 R because translational contribution is always there. Increase the temperature, rotational contribution will come in, and a full R when the temperature is much higher than rotational temperature will enter in. So taking 3/2 R to 5/2 R. And when you further increase the temperature, vibrational contributions will enter in, another R will add up, and you have 7/2 R. And when you capture all these in the form of an equation, we can write this form of equation, that CV, if I further modify, CVM is equal to 1/2 into 3 plus nu R star plus 2 nu V star into R. How to read this? This star, which is represented here, this star means fully active mode. That means this equation, when the temperature, depending upon the temperature you can decide. If all the modes are fully active, then nu R star can be 2 or 3. Let me write down. nu r star, 2 for linear and 3 for non-linear rotor, and nu v star is equal to 1 if the mode is fully active. So, since you are having 2 here and 2 outside, so it is actually giving you a contribution of R. Therefore, this equation is a good equation to estimate the value of CVM. I am not saying to calculate the value of CVM. There is a difference between estimation and calculation. Estimate is an approximation. Why I am saying approximation? Because you can use this expression only if you know whether nu r star is equal to 1 or 0. If you know nu v star is equal to 1 or 0, because there is no intermediate value which you can substitute here from a given temperature. So, what you need to do is you need to compare T and theta and decide. Here you can see theta r, theta v. It is beyond theta v or theta r that full R contribution enters into heat capacity at constant volume. All right. So, what we have discussed, you start with 3 by 2, 1 R adds up for a linear rotor, so 5 by 2 R. Another R adds up for vibration if the temperature is high enough, 7 by 2 R. Now you keep on heating. You have a diatomic molecule. You keep on heating. Vibrations are fully set up. And what happens when you further increase the temperature? The thermal energy is so high that the bond breaks. And that is dissociation. When the dissociation takes place, it is like a phase transition, like the heat capacity at phase transition is infinite. So, when the dissociation takes place, the temperature is used up in dissociating the molecule rather than increasing the temperature. Therefore, heat capacity becomes infinite. What you have? You have X2, a diatomic molecule is dissociating into 2X. That means what you are getting here in the end is 2 times atoms, and atom will only have translational degree of freedom. Translational degree of freedom means only 3 by 2 R. That is what is shown over here. 3 by 2 into 2, which is 3 R, right. So, this is 3 R, twice into contribution due to atoms. To atoms, translational contribution is 3 by 2 R. So, 2 into 3 by 2 R is equal to 3 R. So, this figure explains how constant volume heat capacity changes as a function of temperature for a system which is more than a monatomic system. The expression which is mentioned over here, as I mentioned, can be approximately used to estimate the value of CVM. That means we have to know whether the rotational modes are fully active or they are not active. We have to know whether the vibrational modes are fully active or not active. And why I said that it is a nu v star is for one normal mode. Why I said so? Because if there are more than one atoms, of course there has to be more than one atom for a molecule to vibrate. If it is linear or non-linear, then you have to use 3n minus 5 or 3n minus 6 formula to calculate the total number of normal modes of vibration and then substitute the value over here. This requires a little bit more discussion, but what I have discussed is have given you an exposure to how to treat with the different modes of motion while discussing constant volume heat capacity. We have to consider translation, we have to consider rotation, we have to consider vibration, and if the temperature is even higher, much higher, then we have to even consider dissociation. We will be discussing more about heat capacities by taking suitable numerical problems, but that we will discuss in the next lecture. Thank you very much.